Let's work through this Huffman Coding homework problem. Today's message is, Mrs. May says, Brexit means Brexit. And when someone uses the same phrase repeatedly, you can expect some letters to be more common than others. When we have a message like this to encode using Huffman's method, the first thing we should do, even if the question doesn't ask us to, is count the number of letters in the message. We better not miss one. So that's 5, 10, 15, 20, 25, 27. Okay, now we need to count the number of occurrences of each of the individual letters used in the message. So we've got an M, we've got an R, we've got an S, another M, an A, a Y, an S, an A, a Y, an S, a B, another R, an E, an X, an I, a T, another M, E, A, N, S, B, R, E, X, I, T. Okay, and having done that, let's convert these tallies into numbers. So we've got 3 for M, 3 for R, 4 for S, 3 for A, 2 for Y, 2 for B, 3 for E, 2 for X, 2 for I, 2 for T, and 1 for N. So let's add those up. 1 and 2 is 3, 5, 7, 10, 12, 14, 17, 21, 24, 27. Thank goodness we've caught them all. So we've got our frequencies. The next thing we need to do is to build the coding tree. And remember, we do this by repeatedly grouping the 2 lowest frequency clusters that we have remaining. So we start with each letter being its own cluster, and here we've got a cluster of 1, and there isn't another 1, so we're going to have to group that with a 2 to make a 3. And now we've run out of 1s, but we've still got 2 2s, so 2 2s make a 4, another 2 2s make another 4, and now we seem to have run out of 2s, so we're going to have to move on to 2 3s. 2 3s make a 6. Oh, this is trouble. Another 2 3s make another 6. You've got to be careful to spot those. And we still have 1 3 left, which will pair up with a 4 to make a 7. That's a side of 3s, but we've still got a pair of 4s. So these 2 4s will make an 8, and we're still going. These 2 6s will make a 12. The 7 and the 8 will make a 15, and the 12 and the 15 will bring us back to 27. There's that total again. We can check that. Okay, now to compute the codes, we need to assign a 0 and 1 status to each of these nodes in the tree, and we should do it very carefully to make sure that when we read the codes off, we don't get confused. So I always like to write the numbers near the branching point. So 0 and 1 there, 0 and 1, 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 Okay, so now we have labelled each edge in the tree with a bit. We can read off the codes. So the code for M is 0, 0, 0. The code for R is 0, 0, 1. The code for S, this will be a bit of a bumpy ride. We go 1, 0, 0. The code for A is 0, 1, 0. The code for Y is 1, 0, 1, 0. And its neighbour B is 1, 0, 1, 1. The code for E is 0, 1, 1. The code for X is 1, 1, 0, 0. And for I, we have 1, 1, 0, 1. For T, we have 1, 1, 1, 0. And for N, we have 1, 1, 1, 1. That's the codes read from the tree. Let's just double check that the coding is prefix free. No code is the beginning of any other code. So we're fine. Okay. Let's now compute the length of the encoded message using two different methods. If you've got two different methods, it's good to use both of them so that you can check that you haven't done the sums wrong. So method one is to figure out the length of each code, multiply it by the number of times it's used, and that will tell you how much of a presence in terms of bits that code has in the message. Then we can add them all up. So here we go. This code has length 3, it's used 3 times. That will give us 9 bits in the message. Here's another 3 3s are 9, 4 3s are 12, 3 3s are 9, 2 4s are 8, 2 4s are 8, 3 3s are 9, 2 4s are 8, 2 4s are 8, 2 4s are 8, and 1 4 is 4. Right, let's add this lot up. 3 8s and a 4 will be 28. 9 8 9 8 will be 34. 2 9s and a 12 will be 30. So I make the total of those 92 as the overall message length. So that's the total computed one way. Let's try the other way. The internal frequencies which occur in the tree literally tell us how often we will pass through this node on the way to encoding the message. And each time we pass through a node, we add a bit, 0 or 1, to the message. So the message length must be the total of all of the internal frequencies in the tree. You know, we visit the top node all 27 times. We go left 12 times, we go right 15 times. So let's just add all of these numbers up. We need to add up 27, 12, 15, 8, 6, 6, 7, 4, 4, and 3. Okay, so let's see. 3 and 4 and 4, well, I'm going to do it this way. It makes 11, 7 and 6 is 13, 6 and 8 is 14. Those two make 27, those two make 54. These three make 38, and 38 and 54 make 92. Thank goodness for that. So we've got this message length cooked both ways. One thing you should note, by the way, is that not everybody's tree has to be exactly the same as mine, but you will always get these numbers. The frequencies will always be 3, 4, 4, 6, 6, 7, 8, 12, 15, and 27 in that order. It's the sizes of the groups that matter, not which things exactly are grouped that way. Okay, but now we have an objection from Professor Garble, who complains, but your code for n is as long as your code for a more common letter. And if we look back at the table, we'll see that's true. Our code for n is 4 bits long, and plenty of the symbols which are used twice have codes which are also 4 bits long. And isn't the point that the more common letters get shorter codes? Well, let's ask whether Professor Garble has a point. It's certainly true what he says, but is it a problem? Well, remember, back when we started, n was the only symbol that occurred once, so we were forced to pair it with a symbol used twice. So it's not important exactly that more common letters have shorter codes. What's important is that more common letters do not have longer codes, and that's perfectly fine as far as this is concerned. So we have to be very careful about precisely what the property we're expecting is. More common letters should not have longer codes, but it's all right for the bottom two. In fact, it's inevitable that the 2 least frequent letters will have codes the same length. Okay, that's the end of the question.